Good. Let me double check the sound. That looks all right. Okay, we have a live stream and slides. That's great. There's a sizable mismatch between the number of people in the audience and the number of submissions for the exercise sheets. You shouldn't count Mohammed, who is not officially enrolled in the module, so it's just the three of you. But 10 times as many that submit, something like that. That's fine, given that there's the recordings. Just don't push off watching them. Like, I'm preaching to the choir, I know. I hope people don't push off watching the videos until the very end. I wanted to briefly recap what we've done last time. We talked about vertex cover again, and we're still entrenched in the depth-bounded search tree chapter where we used a bit more interesting reductions or more interesting case distinctions really for the recursive calls. And here, might have to close the door if it gets too noisy outside. Hi. So just recapping what we did last time. We had this very simple special case. If all degrees are at most 2, then you can always find a vertex cover trivially because the graph is so simple. And that means there is always a vertex of degree at least 3. And we use that in the algorithm to have a better reduction of the parameter in the recursive calls. And now we have such a vertex, and now we just pick a maximal degree vertex after the usual reduction rule of getting rid of all the degree greater than k vertices. We can still pick a maximal degree vertex, and then either this guy has to be included in a vertex cover to cover its edges, or else all its neighbors, which we have at least 3. And so we had these 2 recursive calls where we were guaranteed to lose at least 1 in the simple case, but at least 3 in the other recursive call. And then we went into a bit of a rabbit hole about how to analyze how long that takes, or how big the search space still is. I'm recapping that in a bit more detail because we'll build on it in a minute. So just to recall, we had this recurrence in the parameter. We said the problem size doesn't actually matter that much. What we analyze here is really just the search space. And there's going to be some one-off effort to pre-process the graph. So then, yeah, that's the part I wanted to show. We didn't actually analyze T of k, we analyzed B of k, the number of leaves or base cases. And that recurrence was a bit simpler in that it didn't have this extra term here, the red part, which depended on the graph size. Here, everything just depends on the parameter, k. Okay, and then I'm not going to repeat all that. We went from sequences to generating functions, and then the generating functions allows to manipulate terms until you found something where you can go back. And that was this partial fraction decomposition, which unfortunately we couldn't do automatically. Now I've uploaded some Mathematica notebook showing you how you can get the system to do all the computations for you, but you have to kind of manually guide it. Human-guided use of computer algebra gets you there, and you don't have to get your hands dirty with all these complex numbers, but you have to tell the system what to do. If you're interested, or if if people are interested, I can walk you through at some other point. For the lecture, that's all I wanted to show here. And we finished with this kind of black box result that you can use without going through generating functions each time. Whenever you have such a linear recurrence equation, all that really counts is these di, by how much does the parameter get smaller, and then it's the roots of this polynomial. And we applied that to our vertex cover problem, specifically the number of base cases, and got this result for the search space. So that's the base of the exponential growth. And then we had a factor n squared on top. Where does this come from? Well, each of the recursive calls has to do some work. And here, at least, the worst case was we always go down all the way. But then we still had to pay this cost for finding the largest degree vertex of these things. And potentially checking, finding the solution if all the degrees have at most, if all the vertices have degree at most 2. There's a final section in this algorithmic part, fixed parameter algorithms, that I want to briefly mention. It's a nice little trick to combine techniques. Compared to the others, it doesn't improve things by just as much, but it's certainly a simple thing well worth doing. Whenever, if you ever do this in practice, I think this is going to have an impact. It won't reduce the exponential growth though, but we'll see. That's called interleaving, and the motivation is a bit coming from an extreme case that I'll also show you in a minute. So far, the algorithms conceptually had 2 phases. We first applied some reduction rules. I called it pre-processing initially, or kernelization if it has specific guarantees. And so then you end up with a problem kernel where everything is bounded in size by the parameter. And then you solve this kernel with a depth-bounded exhaustive search, where here, I mean, depth-bounded really means there's a parameter where you count down, and as soon as that reaches 0, you stop whether or not the instance is solved. Now, why do we not apply this kernelization each time in the recursive call? In the hope that things get shrunk further and we might get a smaller search space. In principle, this might work, just because usually the reduction rules somehow involve the parameter. And in the recursive calls, the parameter gets smaller. So the reduction rules might apply further than they did initially. That's the key idea. And let's look at an extreme example just to motivate that this sometimes can help a lot. The example, I'm going to admit at the beginning, the example is a bit made up to make the effect extreme, in the way that it's kind of leaving out other obvious things you would want to do in this case. But bear with me for a second just to make the point that interleaving can indeed give you a lot of benefit in extreme cases, and then other cases it'll probably also help, it's just not as obvious. So remember we had where we're still talking about vertex cover. I mentioned vertex cover is the default problem in FPT, where we've already beaten it to death, but there's at least one more substantial result coming next week. And also here, we'll talk about vertex cover again. And we've seen this rule. If you have ever a vertex of degree strictly larger than the parameter, the only option is to take that vertex, because covering all its edges via its k+1 or more neighbors is not going to stay below the parameter. Now let's compare 2 algorithms. The one, algorithm A, is what we've done so far. The catch is we only apply this rule, none of the other reduction rules. And that's a bit stupid, but let's be stupid on purpose to make the effect clear. So only this rule, let me stress that here. So again, you wouldn't want to do this. This just makes the example clearer to analyze. And then we call the same algorithm that we've had before, the simple version, where we just, this was the baby FPT algorithm from all the way back, where we just take an arbitrary edge and say, well, I'm going to include either one endpoint or the other. So I get this 2 to the k as search space. Okay, that's the simple FPT vertex cover. And algorithm B is the same idea, same in ingredients, but interleaved. So we modify this algorithm, keep the same basic recursive structure, but we check whether we can remove more high-degree vertices in each recursive call. And so here's some code how this looks like, because it's so long ago. Simple FPT vertex cover here is as we had it back then. Basically some base cases, otherwise we choose an arbitrary edge, and we take the 2 options. Either of the 2 endpoints has to be included. And then here we can even be smart and return the larger of the solutions. That wouldn't be necessary for just the search problem. Now the interleaved version differs only very slightly. There's this part here where I just created space. So this part is new. Here, that's the reduction rule, right? We check if there's a vertex of degree strictly greater than k. If that's the case, then we remove that vertex, and that's a concise way to put it. I'm setting the graph to the induced subgraph that I get if I take all the vertices except for this vertex I want to remove. Now I'm remembering in this set C for cover that in my solution I have to pick this vertex V. Right, so if I'm returning at the very end some solution, some vertex cover, then I should include this vertex V. So we remember that, but then also we can reduce the parameter because we've included one more vertex, so we have one less more that we can still include. The rest is the same as on the left, except that here also we include this set of forced vertices. Okay. And now let's look at a very specific family of graphs. I called them lollipop flowers for lack of a not used name. This one's super silly, but okay. So it's a family of graphs, GK, where k is some parameter. And then there's a part here where we have these kind of dandelion-shaped flowers. Let me maybe draw the concrete example for k equals 6. So we have a head vertex here, and then there's k minus 2 stars attached, each with k minus 2 leaves. So it seems like I'm drawing k equals 7, right? So I have to draw this 5 times. That's doable. I'm drawing the vertices with different size, but of course they're all in just vertices. Nothing special about them. That's the head. All right, so k minus 2, 1, 2, 3, 4, 5 of these added stars, and each star has k minus 1 leaves, 5 again. And then we attach a tail of 3k plus 1 vertices, so 22. Oh my god, what did I sign up for here? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Okay, got it. This is the tail. Okay, imagine what the graph looks like. Now I'm asking the question, can I find a vertex covered with k vertices? Let's find the minimum vertex cover in this graph. It's not actually that hard. If you start from these guys, it's got to be best to include the centers of these stars, right? Otherwise, I have to include all these leaves. That's going to be worse. So I'm including all those. That also covers all these edges. So these are all done. What vertex is next? What do I have to include in the vertex cover? Yep. You guide me. That one? Yes. Yeah. We have to cover this edge, right? This guy is out because all its other edges are in. And then the rest is pretty boring because now every other vertex has to be included, which will just be all the top vertices. Now, you don't need to count precisely. That's far more than 7, okay? Far more if you want. Now, so that means the instance that we're, I guess I should say, the input is the graph gk and parameter k, threshold k. So all the instances will be no instances, just our poor algorithms don't know about that. Okay, let me copy that. Oh, come on. Good. What do our algorithms do on this example? First of all, I've done the counting for you in terms of the number of vertices. You can count the head, right? You have k minus 2 of these stars, then it's k minus 1 vertices each, plus the one in the center, plus the tail. So we have k squared vertices roughly. If you look at algorithm A, it first applies this reduction rule. Now, the way the graph is constructed, there are no vertices of degree k or larger. So our degree greater k rule just does nothing to this graph. There's no high degree vertices. So because the algorithm otherwise is very, very stupid, it remains at a search space of 2 to the k. And let's make this worst case assumption that we always pick edges from the tail when the algorithm does the recursive, does the random choice, the arbitrary choice. So it'll pick some edge in the tail and include one of the 2 endpoints, decrease the parameter, but it has to try all the 2 to the k options. So the total time will be 2 to the k times the size of the graph to find the edge, or something close to that at least. And eventually it'll answer no, not possible. Our algorithm B, the interleaved version, initially also doesn't do anything, right? And then it picks one edge and nothing happens, and it picks the second edge. So we go down, the recursion tree goes down 2 levels. But at this point, the parameter has gone down to k minus 2. And now suddenly these vertices in the head become high degree vertices. And so in one step, we remove all of them, or to be more precise, we include all of the red vertices, and notice that we already reduced the parameter too much. And so maybe after 1 or 2 further recursive calls, but constant depth, the algorithm can conclude that it's not possible. And this shows you, in this case, you win by applying this reduction rule again, because once the parameter is smaller, it becomes active on a larger part of the graph. Okay? So by and large, we just go a constant number of levels down and we explore a constant search space in this specific case. And so the overall time is essentially linear in the size of the graph. Now, it's a very made-up example. It needs specifically this graph, specifically these algorithms, where we don't apply, I mean, the biggest caveat is, why on earth would you only do the degrees greater k reduction rule and not the one with degree 0 and degree 1 vertices? You would immediately remove this leaf here, and then you would actually remove the entire tail. Right? Okay, but for the sake of the argument, you could have examples like this where interleaving helps a lot. Maybe dandelion would be better. I think that was already taken for some reason. So graph theory people have horrible names, and a lot of them too. Right, the general setup for interleaving. So we've seen this extreme example. What can we do in general? We'll make some slightly more restrictive assumptions than maybe necessary, but this is the part that's nice to analyze. So suppose we have an arbitrary problem, parameterized problem with a kernelization, where now it reduces the problem to a kernel of size q, and that's a polynomial. This is not always the case, okay? But for most of the problems that we've seen, it actually was a polynomial size kernel. At least for vertex cover, we had k squared, I think, as the best. So here, that would be what would be one instance. Right? K squared came from, if you remove all high degree vertices and also all degrees 0 and 1, you're left with all vertices between degrees 2 and k, and so you can't have arbitrarily many of them. You can't have arbitrarily big graphs after you remove all of the vertices of high degree. So we need a kernelization that produces a polynomial-sized kernel and does that in polynomial time. That's standard. And suppose we have a depth-bounded search tree algorithm where we somehow split the input into subproblems with some branching vector. So whatever that looks like. In our vertex cover example, this was 1 and 3. You'll see in the next exercises some more fancy versions of that. In general, that's often a way to improve the exponential growth by splitting up into more cases. And let's also suppose the branching itself, so how to make the recursive calls, is computed in some time, and that's also some polynomial in the input size. From this alone, or basically this part alone, we know that the search space has some exponential size. And this base of the exponential growth, alpha, is just this root of the characteristic polynomial, whatever that is for these di. Okay, it just depends on those numbers by how much do we reduce the parameter in each of the recursive calls. If we now think about the variant A of the algorithm again, we first run the kernelization. That takes p of n time and leaves us with an instance of size q of k. Then we, for each recursive call, in the worst case, have to compute this r of n. So we have r of q of k, because q of k is now the problem size. And so that's for the kernelization. That's the size of the kernel. And this is for the branching. And then we have this for each recursive call in the worst case. What happens if we do it interleaved? You can write down general code for this if you want. The general rule would always be, as soon as the input is somehow bigger than what the kernelization produces, right? This q of k, again, is the size of the kernel. Then it makes sense to run the kernelization again. So you run this kernelization and obtain the reduced instance. And then you do the branching on the reduced instance. And you do that recursively. Like this is to be inserted into your recursive algorithm. Now, if you analyze the running time for this procedure with interleaving, it has the same structure. It's also a recursion depending on the parameter. And for each recursive call, you get a recursive cost for the size of the parameter in that recursive call. But now the extra terms, they shrink with the parameter. Specifically here, whenever the input is bigger than this q of k, and that k is the current k, right? That's the maybe most important bit that's not on the slide. That's the current k, or current parameter. By current, I mean in this recursive call, and it's reduced for further recursive calls. That's what's called L here. So we potentially, in the worst case, we have to run the kernelization in each recursive call. That costs time p. But the input size for that kernelization is bounded by some function of L. And also the branching, which takes time r of the input size, is also now a function of L. The current parameter, not the initial parameter. Okay? It looks like a subtle difference that doesn't make any, hasn't any big impact. The non-leaf version was just this. But it has two kind of implications. One will be it makes the algorithm faster, but to know that, or to see that, it means that the analysis becomes a bit harder. Previously, that's why I went over this before we started with this section again. Previously, we could essentially ignore this inhomogeneous part of the recursion. We just pretended this wasn't here, solved the recursion that is left, and then in the end multiplied by this term, because it was a constant with respect to L, right? It's the initial parameter, so in the worst case, in each recursive call, you have this cost. Now, with interleaving, the cost of this goes down. So if you want to analyze, if you don't want to just upper bound it by the cost without interleaving, you have to include it in the recursion. So it makes the analysis a bit harder first. Okay, as an example, let's look at the same algorithm we've analyzed in detail before. This better FPT vertex cover, which again was the, okay, I think I'll have it on the slide again. So the initial call has potentially a large graph, but then we apply the reduction, buses reduction, removing all vertices of degree 0, 1, and greater than k. And so the resulting graph is at most k squared in size. That's the kernelization at the first step, and then we start the interleaving recursive call. Okay, so there's a one-off cost in terms of the original graph size plus whatever we do in the recursive procedure. Okay, so I don't have the code for this again on the slides. It's the algorithm where we split off the case that all degrees are bounded by 2, in which case we solve trivially what the vertex cover is, or we check whether we can solve it with at most k vertices. And otherwise we branch off, but then we have one recursive call where we reduce the parameter by at least 3, because if I remove the case of all degrees at most 2, one vertex has to have degree at least 3. So the recursive cost for this can be written as some base case, and then for the recursive calls, same contribution as before, but now an extra term that captures finding the largest degree vertex and potentially reapplying our reduction rule. And that's both can be done linear in the size of the graph, and the graph is, in the worst case, quadratic in the parameter of the current call. Okay. Maybe for consistency, I should have called this L here, this K L. That's what it was on the previous slide. But of course, it's just a name for the local variable. Now, the point is, I cannot simply ignore this part if I want to get the tighter analysis. So if we dig into this analysis from before, what we did at this point was go from the sequence tk to the generating function. And I'm only roughly sketching the process at this point. So we said there's, I can write this like this and then split off in the recursion after I shift it. So I'm taking out the first few the base cases. I just leave as a fixed polynomial. This was just what was it? Was 1, right? It was 1 plus z squared in our case. And then for the remainder of the sum, I can insert the recursive equation. Maybe let's do it for the concrete example that we have here. So I'm not going to do the full thing. I'm just sketching it up to a certain point. You'll see in a second why or what that is about. So 1 plus z squared. We said just cost is 1 for these small cases. And then for k at least 3, we can insert the recursive equation. And then you may remember or look up, these two parts essentially led to some shifted and modified version of, again, the generating function. Didn't give that a name, t of z. So the green part becomes some, I guess here we pull out 1 z, and then t of z, and we probably have to subtract some. And then there's a z cubed, t of z. And because I'm starting at 3, so this one's probably fine as is. This one needs some subtraction because I start at 3 when the generating function would have started at 1. But what's new is this k squared. Okay, that didn't exist before. We had a homogeneous recursion where we only had as summands these recursive calls, not anything else. But this blue part can also be rewritten because if you look at it now, this is just some specific sum. And you can again look up formulas for this one. Just to give you a hint of why this could be possible, if you take the geometric series where you have z to the k, you may remember that this is just 1 over 1 minus z. Now let's take the derivative on both sides. Sounds a bit crazy maybe. If you do that here though, it's a sum, so the derivative is taken for each summand. And then you have k in front, and then z to the k minus 1. And here we have to take the derivative as well. There's 1 minus z to the minus 1. So if you take the derivative of that, oopsies, is 1 minus z to the minus 2. That's, and the minus in front. That's the outer derivative, and then you take times the inner derivative, which is minus 1, so that minus goes away again. But really what it says is just 1 over 1 minus z squared. And if you take derivatives another time, then you get something that's very close to the term, to the series that we have here. Then you get, I guess here we can actually sum at 1 from 1 because that first term is 0 anyways. That avoids having this negative exponent. So we have the k from before, and then we get another factor k minus 1, and that's set to the k minus 2. So here we can sum from 2 because all the other terms are multiplied by 0. And here you can take derivatives again. So same game, minus 2 for the outer derivative, 1 minus z to the minus 3, and then again the minus 1 for the inner derivative. So you get a similar type of formula for this series. That's not exactly k squared set to the k. It's k times k minus 1, and then there's a shift with z. But maybe with the kind of simplifications or changes of variables that we've done last time, you can maybe get a glimpse of how you can get from this to the blue one. So to cut things short, what you get from this blue thing eventually is just a function of this form. It's some rational function. So it's a polynomial of z divided by another polynomial of z. Let me say capital for functions. So it's some rational function like this, and we'll actually always have a 1 minus z factor in the denominator. Okay? So we don't even need to figure out in detail how this works. That's not the focus of this class. My point is, you can use the same machinery that we've covered for the linear recurrences last time with generating functions. And you can also solve these inhomogeneous equations, where you just need to find a representation for this series. And to be honest, this one you could just type into Wolfram Alpha and it'll spit out the result straight away. For simple cases like this, no need to do it manually. And so if you do that and do it in the general case, you can again get a result that you can just use as a black box. So if you have an inhomogeneous linear recurrence equation of this shape, same as before, but this additional function added or additional term added, and we assume that this additional term is not too big, it's a polynomial, bounded by a polynomial. Then you can show in full generality, if you take again this characteristic polynomial, that's actually the same as before. That doesn't quite check out. I don't know. This is probably replaced by this. Forget about it. Then you can get an asymptotic representation, an asymptotic bound for the solution Tn in terms of Tn0, where Tn0 is the previous recurrence without this inhomogeneous part. Okay. In other terms, what it says, this light blue part here, it doesn't contribute to the leading order growth. It doesn't contribute to the most significant part of the growth of this recurrence if this stays a polynomial. Maybe intuitively it's kind of clear because the overall growth is exponential in n. Maybe it's clear that if you do something polynomial in each step, that shouldn't harm too much. But you're doing it in each step, so you multiply it with the exponential part, so it's not obvious. The trick why it doesn't contribute a factor f of n times this growth is that also the added term shrinks if you go down the depth, the recursion tree. So most of the invocations of this fn will be at the bottom level where n is constant. That's maybe the intuition. So, but what it means for you really is whenever you have such a linear recurrence and this additional term, the inhomogeneous part, doesn't grow exponentially, you can basically ignore it. You just solve the equation as if it wasn't there. And the result is at most a constant factor of. Let me comment on, just because it's so nice, a little bit of advertisement for this piece of mathematics. You can push this application of generating functions further. So what we've done was we started in sequence length. We had a recursion for a number sequence, and we wanted to know how quickly it grows because it describes the cost of our algorithm. And from the recursion itself, this isn't obvious. So we translated it to generating function length, specifically this ordinary generating functions, and then used basically algebraic equations in this generating function land to modify what we got from the recursion. So specifically here, the recurrence equation gets a functional equation for the generating function, which you could solve and simplify. Specifically, partial fractions was the magic potion here that did the heavy lifting. So you get a closed form for this generating function where you can, in the best case, extract coefficients back. That's precisely, to this point, that's exactly what we did for the vertex cover example. You can push this further by instead first approximating the generating function. And then you only get back, in the end, an approximate solution for your number sequence. But oftentimes, that's the best we can get, because the recursion is so tricky that there's no nice closed form, and it's not even clear how quickly it grows from the get-go. But there's this field called singularity analysis. So a singularity in the function, like, don't think about AI in this case, it's just a point where the derivative of the function is broken in some way, where the function is not smooth. So it could be, for real functions, it could be a point like if you take the absolute value function, it has a singularity at x equals 0, because if you come from the left and come from the right, the slope is different. And that causes problems for the smoothness of the function. Now, in general, you have to view these functions as complex functions, mapping complex numbers to complex numbers. And then singularities are, in a way, both easier and harder to work with. Complex is always less intuitive, but in a way, the theory is a bit cleaner. To cut this short, you can usually find a single dominant singularity, one of smallest absolute value, and you can prove that this dominates the growth of the number sequence that you started with. So what you do is you approximate your generating function by a simpler function plus an error term, which is a big O term, but of a slightly funky shape. So this is for the limit that z goes to z0, not the more computer science usual n goes to infinity. And then from this shape, there are theorems like the one on the next slide that show you what happens if you take coefficients. If you apply this coefficient plugging operation on this thing, you get the coefficients of f, and suppose that's this, and you get some error term that corresponds to the error term. So I know this is, it's impossible to follow this in detail because I haven't told you what all these things mean, especially singularities we didn't talk about. Just in case you're interested, here's some concrete example of what these transfer theorems can look like. There's a technical condition. It's not so important what this means. If you're curious, I can point you to the right places, or I can tell you offline. If you can represent your function, for example, like this, for some real alpha here, and then the coefficients behave in a nice way. The coefficients of f are essentially the coefficients of g with some error term where you get a polynomial that depends on the power here. Okay. And you can extend this further to solve other kinds of recurrences. That's the gist of it. There's a field called analytic combinatorics that pushed this to the limit. No pun intended, I guess. Whenever you have a recursive description of some object, probably there's a way that with techniques from this field, you can get an asymptotic approximation of the numbers from the recursion. So just a little bit of advertisement because we delved into generating functions anyways. Briefly back to vertex cover though. Where we left off was with this recursion that described the cost of our interleaved vertex cover algorithm. Now we just apply the black box theorem here. And what we get is the cost is the same up to constant factors maybe as the cost would have been without this f. We just replace it by nothing. But that's the recursion we've solved last time for the number of base cases, which was exactly this 1.4 something to the k. So we get that now the total time is this exponential. No polynomial factor applied to it whatsoever. There was this, this one step where I said initially the graph can be arbitrarily big. We apply the reduction once, and then comes the recursive part. This is for the recursive part, so we have to add the initial reduction step, but that's all. So we basically transformed via this interleaving technique the cost from exponential search space times a polynomial to just plus the polynomial. Sounds like not such a big deal, but in terms of actual time, it can mean quite a big difference. Okay? And this is, again, the provable worst case. Actual time might be better if you don't always get the worst case recursive calls. The last bit I wanted to mention is that our better FPT vertex cover is not the end of the story so far. People have worked on this more and pushed the exponential growth a bit further down. They also have this plus here, so they're also using interleaving. And so far, this is the best result I could find. It's not clear how far you can push this. It's likely that there is some limit below which it seems there's arguments against pushing further, but I don't think this is reached yet. But the algorithms essentially try more and more cases and more clever combinations. So it gets more and more messy. But in principle, you can push down this recursive, this exponential growth quite dramatically from 2 to the k to 1.2 or 1.3. That's already a pretty impressive result. That's all I wanted to say about this analysis and also the whole of FPT algorithmic techniques for now. A quick summary is what we've seen, the two strategies for designing FPT algorithms. One is the the depth-bounded exhaustive search, where we use the parameter to truncate recursive calls. And the second was kernelizations, where we shrink the problem size using some reduction rules. And we've seen how we can analyze the resulting algorithms. Now again, generating functions are pretty cool, but if you don't love them just as much as I do, you can use the black box theorems, and all you really need is the characteristic polynomial. And interleaving kind of gives this last twist that really the exponential search is all there is in terms of the dominant cost. Any questions on any of the stuff in this unit? If you can't think of something right now, you can always post it on CampusWire as well. Should also check on error with the live stream. There were two people saying on Slido that they couldn't use the live stream properly. I don't know if that's been resolved. It's been a while. From my side, there's no indication that there was any issue. So I'm also supposing the recording is not affected. If you still have problems, maybe tell me again. Otherwise, it's a good time for our break. And then we'll start with a fresh new unit. Hmm. Okay, all good to move on. So of course there was no intention behind it, but it seems the website had the wrong live stream link. I don't know, maybe it was cut off or something like that. Not sure why it happened, but maybe that's a fun reminder that coming in person has some benefit. It's just less that can go wrong. Okay, so time for new unit. We stay in the realm of parameterized algorithms and complexity. But now we'll look at the other side of the story. We've seen some techniques for designing algorithms. And if we try them on a problem and they don't seem to work, then we may get the feeling that we're trying something impossible. How can we build up evidence for a problem not to allow an FPT algorithm? That's what we'll look at in this case. And there's some nice theory that helps you with this. I think it's going to be much shorter than the previous unit, but maybe a bit less intuitive at some points. But I'll focus essentially on the parts that allow you to do the specific reductions that are most useful. In the next unit, we'll look at parameterized reductions to show that a parameterized problem, probably doesn't allow a fixed parameter algorithm. And this is complementing the previous unit of algorithmic techniques to design FPT algorithms to show that in some cases it seems unlikely that we have any fixed parameter algorithms for a given problem. And we've already seen some examples of these problems where in the previous chapter I initially introduced the problems at the beginning, but then they never popped up again in any of the techniques. We've talked a lot about vertex cover and some versions of satisfiability and this closest string problem. But then there were some other graph problems where I was suspiciously quiet about. And we'll see in this chapter why. As I said, it's going to be shorter than the previous chapter, but we have to cover a few more abstract concepts for reasons that will become clear after the first attempt. Maybe I'll leave it at this mysterious remark. The goal would be to prove that a problem is not in the class FPT, in which case we shouldn't try finding an algorithm that has a FPT runtime. Clear. So one example that maybe you've noticed wasn't popping up in the last chapter was the clique problem, parameterized in the canonical parameterization of the problem, so parameterized by the threshold itself. Does a graph have a subgraph of size k, or does it contain k vertices that are mutually connected? And it seems indeed that no FPT algorithm can solve the clique problem. But how would we prove this? In particular, with the usual problem that for the maybe not so likely case that p equals np, but at least it's still a possibility, we cannot possibly prove such a statement. If p equals to np, then all of the problems that we discussed here, all problems in NP are also in P, and then of course they're trivially also in FPT, because any polynomial time algorithm is also a fixed parameter algorithm, an FPT algorithm. So the strongest kind of lower bound we could possibly hope for, given this uncertainty, whether P is equal to NP, would be something conditional on the assumption that P is not NP. That's the least we need. We'll actually seem to need more. This is not going to be sufficient. In another way, going back to classic complexity theory, this is the standard assumption. You would say things like, there is no polynomial time algorithm for the clique problem without the parameterization unless P equals NP. Right? because click is an NP-hard problem, we know that that statement is correct. Either P is completely equal to NP, or there is no polynomial time algorithm for click. Okay, so more abstractly, that's the kind of statements we'll have. No algorithm has a certain property, whatever that will be, FPT algorithm in this case, unless some hypothesis from complexity theory fails. And it could be P not equals NP, or it could be slightly stronger assumptions. In the first part, we'll look at reductions. Namely, they were the key tool in classic complexity theory to avoid having to talk about things we cannot possibly prove. We said instead, let's just relate the hardness of problems to each other. And we certainly will try the same for fixed parameter problems or parameterized problems. So can we somehow compare the relative hardness of these problems? And the thing is that we need somehow a notion that takes the parameter into account. Otherwise, it's not going to make interesting statements. So to preserve the existence or non-existence of FPT algorithms, such a reduction has to keep the parameters small in the produced problem. So you take a parameterized input of one problem, an input and a parameter, and you output via the reduction the input to another problem, then that also has a parameter, and that shouldn't be too big. Otherwise, intuitively, you can't make statements about FPT algorithms. And more precisely, this is a very natural way to formalize this. You have two parameterized problems. L1, remember this is a language, it's a decision problem, and kappa is a parameterization, a function taking an instance from the strings this talks about, so from sigma 1 star here, and it gives you an integer, the parameter of this input. So we have two such parameterized problems, and then an FPT reduction from L1 kappa 1 to L2 kappa 2 is an algorithm or a function, a mapping that takes some word in where this L1 is taken from, produces a word that L2 is taken from, so that for all inputs to this mapping A, we have that X is in language L1 if and only if the output from the mapping is in L2. That's precisely as in polynomial time reductions. Then polynomial time reductions, as the name says, had to run in polynomial time. Here we allow FPT time. So the algorithm A that performs this mapping can take FPT time, so it could take more time if the parameter is big. And now the third part, this is the new bit. It has to be parameter preserving. So concretely, the parameter of the output has to be bounded by some function of the parameter of the input, but not the input size. Right? So this one here does not depend directly on the size of x, on the length of x, but only on its parameter. Okay? If such a mapping exists, then we write in analogy to how we had it. We had less or equal p as the notation for a polynomial time reduction from L1 to L2. So we write less or equal FPT for such a parameterized reduction. This is essentially the natural definition if you think about this requirement, analogous to how we defined FPT time. So far, no big surprises, okay? Let's see some example. First of all, if you just take some classical reductions, they may not necessarily be parameter preserving. So as an example for this, let's look at the vertex cover problem and the independent set problem. Just to remind you, vertex cover, well, we talked about it a lot. So here you have to find the smallest subset that covers all the edges. What can I do here? I gotta pick one of those two, I guess. So I need 3, right? I can't possibly do it with 2 vertices. But vertex cover was find a subset of vertices so that all edges have one endpoint in the chosen set. An independent set, let's take the same graph. A maximal independent set is a subset of vertices that are not connected in any way. So what's a maximal independent set in this case? This looks like a good one to pick. Maybe this one, and I guess I can't do 4, or can I? It doesn't look like it. I don't know if you see a larger one. A classical reduction between these problems from classical complexity theory, we can prove that independent set can be polynomial time reduced to vertex cover, for example, with this reduction. The graph for vertex cover is the same, and the parameter is the number of vertices minus k. So you're given an instance of the independent set problem. I'm just making up some arbitrary graph here now. It's not anything special. And some threshold k, right? So let's say k is equal to 5. Can I vertex cover this with 5 vertices? Oh god, okay. I'm gonna take this, gotta take this. Then this looks like a good one. Then almost everything's covered, right? Just these two. That covers everything. So I could do it with 4. I might as well just include another one. I could, or not. Doesn't matter. Now the thing is, if we take this parameter for vertex cover, the reduction says we should take the number of vertices, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, minus 5. And then this claims there is a vertex cover of 5 vertices if and only if there's an independent set of 4 vertices or more. So vertex cover at most 5, independent set at least 4. And the trick is to just take the complement. I think I can't count, right? 1, 2, 3, 4. Okay, because I didn't. Let me do what I did before. So let's add the 5th vertex cover vertex. The simple property I'm using here is if the red set is a vertex cover, the complement set of vertices has to be an independent set. Because if there was any edge between those blue vertices, then that blue edge would not be covered by the red vertices, right? And this is an if and only if. Now that's a fine reduction in classic complexity. It also goes the other way around by the same trick, but it doesn't preserve the parameter. If your graph is huge and k is small, then you have a small parameter initially, but the output parameter is huge now. So you cannot bound it by just a function of k. Yeah. All that says is you have to work harder if you want an FPT reduction. So in particular, this does not imply that the parameterized problem P independent set is FPT reducible to P vertex cover. Because that that reduction is not parameter preserving. It could be there's another one in principle that shows this, but in this case, actually, we don't believe it is true. So this statement probably isn't true. Let's see another example where things do work. So where the reduction is parameter preserving. As a boring reduction too, but as a simple example to make the point, we can reduce the independent Z problem to the clique problem, also in the parameterized sense with an FPT reduction. And again, this reduction works both ways. And the reduction is simple. I have some graph as input graph. I'm not going to make it too big now. So maybe this is your input graph, and now you ask for an independent set of size, I don't know, 3. That should be doable by picking, no, it should not be doable. Okay, so no instance, fair enough. Now you're taking the complement graph, where you add all the edges that are not in the original graph. I guess that gets too messy. So the complement graph has this edge, and this edge, and this edge, and this edge. I'm just counting degrees. Seems that's all. The 3 here belongs on this side, but we actually do the same parameter. So now the thing is, if this has, let me take a parameter 2 where it's a yes instance so we can draw it. If we can find an independent set here, like these two, then we can find the 2 clique in the other graph, and it's trivially this one. It's not super exciting, I guess. Because with just 2 vertices, it's a single edge. But you get the point. An independent set exactly means no edges. A clique means all edges. If you just take the complement graph, one turns into the other. But we've not modified the parameters, so it's obviously parameter preserving, even in a very literal sense. The important bit is just that k prime is bounded as a function of k. Certainly true in this case. Okay? So this means the independent set and clique problem are also in the parameterized sense equally hard. Okay. We've defined reductions. The next bit is to define hard problems or complete problems for a certain class. That's how we went from polynomial time reductions to the notion of NP hardness and NP completeness, which gave you this strong statement, right? The one for all for one. Either this single problem has a polynomial time algorithm, or all of NP doesn't have. So we'll try to do the same thing for these parameterized reductions. So we need an analog of NP. We know, or intuitively, FPT is playing the role of P, the efficiently solvable algorithms in a parameterized sense. But we need the kind of superset of things that we cannot really solve efficiently, but we have to somehow have a universe of problems to talk about. And that's not as obvious what to pick here, but one choice could be this class that's been called para-NP, so parameterized NP. I think it's a natural definition. You say we still allow FPT algorithms. And remember when we went from P to NP, we said instead of polynomial time, we now allow non-deterministic polynomial time, where we allowed the machine this magic guessing operation, where it could essentially, with divine insight, take the right of two paths without knowing which one it is. Formally defined in Turing machines as there's many possible computations, and if any one of them leads to an accepting configuration, the overall input is accepted, even if there's one out of exponentially many. So the same we can do here. We allow a non-deterministic machine, a non-deterministic Turing machine, but we allow it an FPT number of steps. Right? So same as before. That's some function of the parameter that's arbitrary, and then a polynomial in the input size. Same notion as before. Indeed, this class has a few promising properties. I'm not going to prove those. You'll see soon why. First of all, it's closed under FPT reductions. What's that supposed to mean? Well, if I have a problem and I can reduce the problem, so say some problem A is in para NP, and I can reduce some other problem to this problem A, then I know B is also in para NP. Another nice consequence is FPT is equal to para NP, which again, we shouldn't think is a likely thing. Right? This means I can use the full power of non-determinism in an FPT algorithm, and that doesn't allow me to do more than doing it deterministically without any guessing. But the two are the same if and only if P and NP are the same. So it's kind of a strong way of saying if I have problems in there, unless P is equal to NP, I won't have an FPT algorithm. And you can also prove something similar to a kernelization for this class. So you can, again, transform this general FPT time into a pre-processing step, and then a something that's just bounded in terms of the parameter. And because the class is so analogous to NP, we can also define hardness in the same way. We can say a parameterized problem is para NP hard if every other problem in para NP can be FPT reduced to it. Exactly the same as we defined NP hard. Every problem in NP can be polynomial time reduced to that problem, then that problem is NP hard. So same thing here, except that we have to carry through the parameterizations and use FPT reductions. So we should be happy because that sounds like a nice theory. It has all the good properties we would want of a complexity class. And it seems to nicely play with P and NP. Now, the problem is that it actually plays too nicely with P and NP. And let's prove this theorem, and then I'll give you the interpretation afterwards, because the proof nicely shows the absurdity of para NP completeness. So formally, the statement is as follows: we have some non-trivial parameterized problem. Non-trivial just means it's not everything a yes or everything a no instance. That's all that means. So with some parameterized problem that is para NP complete, then indeed the restriction of that problem to bounding the parameter by some constant is NP hard already. I guess this is a bit sloppy. There exists a constant d so that the restriction is already NP hard. Let's see why that might be the case. So we got to work with what we have, right? So let this L and kappa be and para NP hard or para NP complete. We need it to be, well, it is para NP complete, so let's not worry about it. And let further some other language, let L prime be NP complete. So we have to somehow connect these two. So we'll define a boring parameterization, kappa 1, that just outputs 1 for every input. It's the constant parameter. Well, if L prime is NP complete, that means L prime and kappa 1 is in para NP. Why? Well, we have to show that there's a non-deterministic FPT algorithm for this parameterized problem. I should say non-deterministic. Because the problem is in NP, there is a non-deterministic algorithm to decide it in polynomial time. And that same algorithm is also FPT time, because FPT includes polynomial time. And we actually don't need the parameter to be anything. It can be 1. That's what it says here, to use kappa 1. So the same algorithm is also a non-deterministic FPT algorithm for this parameterized problem L prime and kappa 1. Right. Now we use that we have a para NP complete problem. So there has to be a reduction from this problem to L kappa. No. Which means there's some algorithm, I haven't used the name for this, so there exists an algorithm A. Just going from the definition of FPT reduction. So x is in L prime if and only if A of x is in L. That's the equivalence. And the running time of A has to be FPT in the input. So it's f of kappa 1 of x for some function x and n to the c, or say size of x to the c for some constant c. But really this means just a constant factor, because kappa 1 is always 1, right? So whatever f does, it can only be some number. Yeah, I was a bit ambitious with the space here, I think. So this is actually it's polynomial in the size of the length of x. Well, that's essentially it, right? So okay, this internal here is 1. That means f of 1 is some constant. Let me use my my new page now that I made it anyways. So the running time of A is actually polynomial in x. And that also means we also have an algorithm B for our parameterized problem here. Let's put that here. So because L kappa is in para NP, there's an algorithm B deciding L in FPT time, some function f prime of k times n to the c, n to the d, whatever. Let's say c prime. Now we're just chaining these two things together. Okay, we could take an input for L prime, we map it via A to the problem L, and then we take this FPT algorithm B to solve it. So if I take B and apply it to the output for A, this decides L, L prime. Sorry, that part is useless because that's a non-deterministic algorithm. Forget about it. I don't think we need that. The thing is that we reduce this NP-hard problem to a slice of L where the parameter is bounded by a constant. And so A itself it maps this NP-hard language L prime to a language L lesser equal D, where D is just f of 1. That's exactly our unknown constant, but it's given by f of 1, some constant. That's the set of all inputs in L where the parameter is bounded by this constant. So L transforms this NP-hard language to this language, and it's a polynomial time reduction because its running time is polynomial in the input size, right? So what we've actually shown is that L prime polynomial time reduces to L lesser equal D. And that was an NP-hard language. So also this one is it's NP-hard. Okay, I'm gonna try to write it a bit clearer. And that's all we wanted to show. And this part is correct, but useless. Sorry for the confusion. Right, so we've shown whenever a problem is para-NP complete, already the restriction of the problem where the parameter is constant has to be NP-hard. So what this means is that really almost no interesting problems are para-NP complete. They cannot be. In particular, all of these cannot be para-NP complete because if you bound the parameter by a constant, the resulting running time is polynomial. Remember, for each of these problems, a trivial solution is to go through all subsets of size k. That's an n to the k algorithm. It's not polynomial, it's not FPT, but if k is a constant, then it's polynomial. That's the important distinction between FPT and what's also sometimes called XP. So the problems where if you bound the parameter by a constant, then the resulting running time is polynomial. These are much weaker guarantees than FPT. Okay. I'm not officially introducing XP, but that's these problems. So you could say it's n to the order k, or even worse, I guess. But that's what the running time for these is. So this notion is much too strict, and it won't help us for the interesting questions here. So problems where there's some hope to get a good algorithm, but it doesn't seem to work with an FPT time. It doesn't help us tell why that is the case, why these problems don't really seem to allow an FPT algorithm. So we'll have to brush up the theory a bit to make that distinction. There are problems that are para-NP complete, for example, graph coloring, or the parameterized P graph coloring is para-NP complete, but that's virtually just the case because also 3 coloring, where the parameter is 3, is already NP hard. Okay, good. Let's leave it at that. And for the fun of how to improve the theory, we'll have to wait for tomorrow.